Hi, I'm Chelsea, and today I'm going to demonstrate definite integration. Okay, so for definite integrals, what we're using is one of the parts of the fundamental theorem of calculus. And this says that if we have a function f that is continuous on the interval from a to b, and f of x is the derivative of big F of x, then if we integrate on that interval from a to b of f of x dx, it is equal to big F evaluated at the endpoint b minus the function big F evaluated at the endpoint a. So essentially, and this is a very, very powerful theorem, it says that the integral of some function that is the antiderivative of another is equal to that function, the big one, f, the original function evaluated at each of the endpoints, the difference of that. Okay, so let me demonstrate how we use that with an example. So in this example, I have chosen the function x squared minus 1 over x, the quantity squared, and we're going to integrate that on the interval from 1 to 2. Now, the first part of the fundamental theorem that we often forget, and especially when we start to learn this, sometimes we don't realize we need to know this, is that this integrand has to be defined, or has to be at least continuous, from 1 to 2. Okay, so every single point. So we can't have anything where it's undefined. And that would flare up in points where we have maybe a denominator equal to 0. And in that case, what we have is actually an improper integral. And there's some other steps we have to do in order to evaluate that. In this case, our integrand is continuous on this interval from 1 to 2. The only point we'd have to worry about is where x equals 0, and because we have an x in the denominator. And fortunately, that is outside our interval. So we are going to be able to use this theorem. Okay, so we're going to just try to integrate this. What I'm actually going to do, and the reason I chose this was to just demonstrate how we can use a little algebra to make this easy to integrate and define the antiderivative of. So what I'm going to do is simplify this inside first. Okay. And 1 to 2, I'm not going to lose any parts. So we have a monomial in the denominator, so what I'm going to do is simply divide that into each term, so we'll be left with an x there, and we'll have a minus 1 over x, that quantity squared dx. Simplify that a little more, I'm going to multiply out this binomial. Okay, and what we'll have is x squared minus, multiply the insides and double it, so that would be minus 2, and then square this last term, 1 over x squared dx. Okay, and now we have a simple trinomial, and we can just use the reverse power rule on each of these terms to find the antiderivative. Note that this thing is actually x to the minus 2, and that'll just help us in the long run. So I'm going to take the antiderivative of everything. What we'll have from this first term is x cubed over 3. From the second one we get a minus 2x. And from this third term, when we take the antiderivative, we'll have, raising the power by 1, a minus x to the negative 1. This minus 1 comes from that bottom part, where we get a negative 1. And we're going to say we're evaluating all this from 2 to 5. I'm sorry, from 1 to 2. And notice that I don't have a c in here. That c only comes from indefinite integrals where we are not evaluating on an interval. Okay? But as soon as we have this interval, we need to make sure that we keep the endpoints so we know at which ends we can evaluate. Usually I like to write it like this, where I have brackets that enclose the entire thing of which I'm going to put in these values. Sometimes you'll see simply a straight line at the end of the expression with the endpoints there. But again, I think especially if you start splitting up your integrals, it's nice to contain everything so you know what values go where. Or especially if you use substitution and we actually have to change those values of these endpoints. Okay, so once I have that, then what I'm going to do is this function inside is our big F that we talk about. So first I'm going to take this 2, the b, and I'm going to stick it inside this whole thing, everywhere that I have an x. So what I'll get is 2 cubed over 3 minus 2 times 2 minus 1 over 2. Again, I just dropped that down because this is really 1 over x. Okay? That whole thing minus, okay? So this part that we did right here would be our f of b, where our b is 2. So now what we have to do is go back into this thing again and stick in our a, our 1, okay? So we'll have 1 cubed over 3 minus 2 times 1 minus 1 over 1. Okay? Alright. And it's very important that you always have the top value put in to your function and then you subtract from that the bottom part. Otherwise, we would, if we took the bottom and subtracted it from the top, we would get a negative of what our answer should be. Now at this point, all we have to do is simply simplify what we have here to get just one value. So that's all I'm going to do is just subtract some fractions. So 2 cubed would be 8/3 minus 4 minus 1/2 minus 1/3. I'm going to just distribute this negative sign, plus 2 plus 1. And when we add up everything together, we actually get the value 5/6. And there is our answer. So with definite integrals, typically what you will get is an actual value, an answer. Because what it is doing is it's evaluating that area under our curve. So under this function, okay? And area is a value. It's an answer, especially when we have endpoints. Again, we don't have a c appearing because it's not indefinite, so we don't have a family of curves. We can actually find the exact value. And that's it. For more information, please visit our website at www.sandersontestprep.com. The link is in the description box below. Thank you.